We're looking at some questions in the textbook from page 13, probably goes 13, 14, 15 kind of thing, but starts on page 13, and then some multiple choice numerical response questions. We talked yesterday about a general idea of these parameters, h and k, being things that can be found by using an ordered pair and substituting that ordered pair into the equation. So for example, if you're told in question 6 here from the textbook, if you're told in question 6 that there's a vertical translation that's applied to y equals x squared, you should know that since x squared is f of x and a vertical translation results in this new equation, that when you put those ideas together, you end up with the new equation of the transformed function being that. And, you know, we've had this conversation a couple of times. You probably don't need to write f of x plus k. You probably understand it's x squared plus k. But the point is that's a missing parameter. And if you're told that the graph passes through the point 4, 19, what that tells you, and this is something that's maybe missed by people when you talk about graphs, it tells you that when x is 4, y is 19, and that's why that's one of the many points on the graph. Both of those numbers put into the equation at the same time give you a true statement. I'm not going to do this. You would put 4 in for x, you would put 19 in for y, you would simplify that and solve that for k, and that would give you your answer. If you got k equals 3, then the answer is it shifted 3 units up, and I believe the answer is 3. Yeah. Because you'll have 19 equals 4 squared plus k, 19 equals 16 plus k, k is 3. Similarly, if you have this situation, what horizontal translation is applied? Well, you know that a horizontal translation results in this new function. So since the function is f of x equals x squared, you would have x minus h quantity squared. But again, you're given the coordinates of a point, namely 5, 16, which means that when you put 5 in for x, you have to get 16 for y. I'm just going by memory here. I think the answer in the back only has one answer in this question, but it should have 2. There are 2 answers. And if you're getting only one, so there's an error in the textbook. If you're getting only one, you're making the same error that whoever made the key made. There should be 2. Because, and I'm going to take this one just a little bit further, we'll have 16 equals 5 minus h quantity squared. There's 2 paths that you can walk down now to find out what h is. One of the paths is for you to take the square root of both sides, remembering that for the number you go plus or minus, and you end up with plus or minus 4 equals 5 minus h. And now, that's just one path you can take, but it branches off now into 2 equations. This one path has 2 solutions. One of the solutions is going to be what you will get when you solve this equation, and one of the solutions is going to be what you will get when you solve this equation. And I'm not going to spend time solving those equations. They're 2 linear equations. You'll get 2 different answers. Okay? The other path you could take is to FOIL out or multiply out or expand this binomial squared and get 25 minus 5h minus 5h plus h squared. What's happening in my brain there is I'm saying 5 minus h quantity squared is 5 minus h multiplied by 5 minus h, and I'm foiling that out. That's why I said I'm going to FOIL that out. And then you're kind of in a Math 20 frame of mind because you see it's quadratic. Quadratic equations are solved primarily, well, I really want to say all of the time the useful way to start solving a quadratic equation is to zero the equation. Or you want to set it equal to 0. You want to move all the terms to one side. So I have h squared, I have minus 10h, And then I have 25 minus 16. I believe that's 9. How's my arithmetic this morning? Looks okay. All right, and then you would say, well, I'm going to factor this. I'm looking for two numbers that multiply to give positive 9 and add to give negative 10. Well, if they multiply to give a positive and add to give a negative, they better both be negative. And the numbers are negative 9 and negative 1. And then what you do is you say, well, h minus 9 equals 0, and h minus 1 equals 0. And if you solve these two equations, you'll get the same answers as if you solve these two equations on the right. Okay? This is maybe a more direct approach. It's quicker because in a way it's already in a completed square form. You just have to take the square root of both sides to get rid of the squared. You don't have to worry about factoring. Now that leads us to this question, which this was basically where I left off with my explanation on it yesterday, that if you have a parabola and you know that it passes through 2 points, now, granted, you do have to understand that zeros are x-intercepts, and that means they're points on the x-axis, and we're going to talk extensively about the x and y axes today, but points on the x-axis have a y-coordinate of 0. In preparation for what we're going to talk about later, let that sink in. A point on the x-axis, any point on the x-axis, will have a y-coordinate of 0. If I were to draw a graph, and this is not really important for this question, well, it kind of is, but I'm stressing it for a number of reasons. If I have this point, or this point, or this point, or this point, these are all points with different x coordinates, but they all have the same y coordinate. They have y equals 0. So the x-axis is where y equals 0. Anyway, we do have to understand that the zeros being 7 and 1 tell us this piece of information from a tabular standpoint. That when x is 7, y is 0. When x is 1, y is 0. So if there's a horizontal and vertical transformation or translation, going back to 6, there was vertical only. So we had plus k, f of x plus k. Looking at number 7, we had just horizontal. So it was f of x minus h, end of the story. Here we have both, so it's y equals f of x minus h plus k, and since f is, I'm actually going to write this here, it's y equals f of x minus h plus k, and since f is squaring, it's x minus h squared plus k. Anyway, we put the numbers in and you have these two equations. This is a system of equations. You first learn about systems of equations at the end of Math 10C. But at the end of Math 20-1, you also do systems of equations that are quadratic, and that's what this is. My thinking here, and I have more experience, I understand that. So I'm telling you that my experience tells me I would FOIL out those quadratic binomial squareds first. Because if I subtract them now, the k's will disappear, and that's a good thing. But then I'm going to have this squared minus this squared, and students can easily confuse what's happening there when you're subtracting. Okay? So I'm going to show you a different way to do it. This equation becomes 0 equals 1 minus 2h plus h squared plus k. And I don't want to just sweep that under the rug as if it's obvious. What I've done is I've taken 1 minus h, and in my head I've said it's that. So that's what I get. Okay? But I'm saying to you that many of you, hopefully, can square this 1 minus h quantity squared to get this without writing anything else down. Many of you. Most of you ought to be able to get what I've underlined by at least writing this down. Some of you may need to actually go first, outer, inner, last, and put it together on paper. But the expectation is, since this going from here really to here is grade 9 math. Pushing the limit, I can say maybe just grade 10 math. It's something that we have to say you need to know how to do. You can't afford to make these little mistakes, and it becomes more problematic at this level because as you get to grade 12, there's more of the other stuff you need to keep track of, right? But this is a pretty big one. When I do the same thing here, I get 0 equals, well, I mean, it's 7 minus h, so I can change this to 7. But what I'm going to get is 49. I'm going to have minus 7h, which is minus 14h. And then I'm going to have plus h squared, and then plus k. And just because I don't like how things are lined up here, I'm going to just do that. Okay. Now, are there any questions to that point? You understand that subtraction is more complicated than addition? Even when you first learn about subtraction, it's harder to think about. I don't like the idea of subtracting equations here. If we subtract these equations, it's going to be a brilliant move because the k's will disappear, the h squareds will disappear, and I'll be able to have a single equation that has h in it that I can solve for. So I am going to subtract them, but I don't like the concept of subtracting because if I do this, then you have to go 1 minus 49, negative 2h minus negative 14. It's complicated. So what I do, and if you had me for a teacher before, you will know that this is my preference, is since this is positive h squared and positive h squared and positive k, I'm going to multiply one of those equations by negative 1 and add them. So if I multiply the top equation by negative 1, this becomes negative, this becomes positive, this becomes negative, and this becomes negative, and adding things is easier. I'm not as likely, and neither are you, to make a mistake when you're adding things as you are to make a mistake when you're subtracting. And by the way, right now, I am in the same kind of mode that you people in my Math 31 class know I was in yesterday. And the mode is I'm teaching math right now. I'm not teaching content. I'm not teaching you about transformations. I'm teaching you math and improving your math skills. So now when I add these, I get 48 minus 12h is 0. These two add to give 0. These two add to give 0. So now I can solve for h. 12h equals 48. H equals 48 divided by 12. Last I checked, I believe that's 4. And now what I have to do is go back to any of these equations that I see here that connect h and k and find out what k is. I mean, I might just go to this equation. 0 equals 7 minus 4 quantity squared plus k. That's 0 equals 9 plus k, because 7 minus 4 is 3. And when I square 3, I get 9. So I subtract 9 to the other side, and I get k equals negative 9. So apparently, not apparently, it's a fact. If you take x squared and you shift it 4 units to the right, and you shift it 9 units down, it's going to have x-intercepts at 7 and 1. And you could check it out on your calculator if you want to. But as I said, I believe I said it in this class, the nice thing about this missing parameter thing is you change the problem from some kind of puzzle to algebra, and algebra doesn't lie. Unless you make a mistake, then, but that's your problem, not the algebra's problem. So I've spent a lot of time going over this missing parameter thing because it is important, and it's going to crop up again and again. And the concept of ending up with 2 equations with 2 unknowns is going to happen again and again. In this unit, the next unit, the next unit, etc. Does anybody have any other questions, though, you would like me to go over from any of the assigned problems? All right. Let's move on then. We're going to be looking at section 1.2 today, and tomorrow. So 1.2 deals with what are called stretches and reflections. What we're going to be doing today is looking at reflections. So this is found on page 8 of your unit handout. We're going to be graphing functions if we take an original function and we reflect it either across the x-axis or the y-axis. And I'm going to tell you right now that the underlying ideas here are very basic, but there is one thing that no matter how I try, no matter how many posters I put up in the room about it, no matter how many times I stress something, some of you get backwards continually. And my dream is that nobody gets it backwards on an exam. But even just this last semester, people came out of the diploma exam and they went, oh, I flipped it, and I shouldn't have flipped it. Good students. So what you want to do is try to be in that larger group of students who doesn't make this mistake. Okay? And when the mistake rears its ugly head up here, I will point it out to you. Okay? It has to do with the axes and labeling the axes and understanding their roles and reflections. So we're going to be graphing resulting functions if we reflect it across the x or the y-axis, or both, determining equations of the new function if there's a reflection, and then we're introducing something new called an invariant point. And an invariant point is a point on the original function that doesn't change when it transforms to the new function. And the reason why we didn't talk about that yesterday or the day before is when you take a graph and you translate it, every single item on the graph moves. Everybody moves. Nobody gets to stay where they are, but not with reflections. So to begin with, what a reflection is a transformation that flips. That's just a different word for reflection. Each point of a graph across what's called a line of symmetry. And if you want, you can think of that line of symmetry as being like a mirror. So when I stand in front of a mirror, the tip of my nose gets flipped across to the other side of the mirror. The bottom of my earlobe gets flipped or reflected from this side of the mirror to the other side of the mirror. Points that are on the line of symmetry, so the line of symmetry is the mirror, but points that are on the line of symmetry don't move. I mean, you can do this if you can't visualize what I'm talking about here, go home and do it. You go in front of the mirror and you do that. And you stand there. Make sure nobody's watching you. And you look at your hand and you say, well, my elbow is a certain distance away from the mirror in reality. And if I could melt through the mirror, my image's elbow would be that same distance behind the mirror. Are you with me on that? Unless it's a funhouse mirror, one of those that is all distorted, right? And I could say the same thing from my wrist, and I could say the same thing from my shoulder. And I could say the same thing for this knuckle on my finger. But the very tip of my fingernail that's touching the mirror will be in the same location as the tip of the fingernail on my image. It doesn't move. It's in the same place. So an invariant point is a point that's on the mirror. Any point that's on the line of symmetry is not going to move. So today we're going to be looking at horizontal reflections across the y-axis. So here's the first thing that we got to really think about. When you see the phrase y-axis, you think vertical, because it's a vertical axis. It is a vertical axis. But when we reflect things across it, it goes from this side to that side. And that's a horizontal change, right? If the y-axis is a line that's running vertically down and intersecting my nose, the tip of my nose, and I reflect this hand across it, it ends up here. It's a mirror image. But that's a horizontal reflection. So a horizontal reflection is across the y-axis. A vertical reflection is across the x-axis. There's a third type of reflection, but we're going to just not talk about it today. I don't want to just, again, hand wave this away as if it's unimportant. I think it's very important. We're dealing usually with functions, and this happy face is not a function, but it's a picture, okay? It's not a function because it will fail the vertical line test. If I look at that, if I take that red face and I flip it over on the other side into quadrant 1, I've horizontally reflected it, and it is across the y-axis. So we're starting to get into the where students make a mistake. A horizontal reflection is across a vertical line, the vertical axis. But there's something trickier, and I'll just show it to you first. That's the y-axis, right? What's the equation of the y-axis? It's a line, it has to have an equation. Well, it's x equals 0. And this is something that I know students, you learn about this actually in grade 9, horizontal and vertical line equations. But the equation is x equals 0. So look at what's happening here. And this is not good for people who just want to memorize stuff. This is great for people who think about stuff. And I have to think about this every time. When I say a horizontal reflection, I picture something like what's on the board. I picture this kind of thing going on that you can see me doing with my hands. And I say, well, what's that across? And I say, well, that's across this axis, and that's the y-axis. And then I say, slow down, Paul. What's the equation of the y-axis? Well, look, here's the y-axis. Over here, x is negative. Everywhere over here, x is negative. Any point to the left of the y-axis has a negative x coordinate. Any point to the right of the y-axis has a positive x coordinate. So any point on the y-axis has an x coordinate that's 0. And I think what people do is they don't think enough here. They go, okay, I know that I have to flip something around. I know that this is horizontal, so I have to flip it and I have to say it's the y-axis. But then you actually have to flip it again and say the y-axis is related to x. So you start off with horizontal, which is an x concept. You then say it's across the y-axis, which is a y concept. And then you say the equation of that is x equals 0, and now you're back to x being an idea that you're using. You are going to have to come to grips with that. And I'll give you an example here. I will give a numerical response question on the exam where you have 3 numbers that you have to fill in. 1 is x equals 0. 2 is y equals 0, and 3 I don't want to talk about because we haven't learned it yet. And a third of the class will write 2 where they should write 1, and 1 where they should write 2. They get it backwards. A third is maybe an exaggeration. You don't want to make that mistake. A vertical reflection is what you're looking at on the right, and that's across the x-axis. There's the x-axis. What's the equation of the x-axis? Well, every point above the x-axis has a positive y value, and every point below has a negative y value. So the equation of the x-axis is y equals 0. And you need to sort this out. Okay. All right. What's an invariant point? Well, if I go back to this, look at the horizontal reflection. Every single point on the red image on the left side of the screen moves. And that's because every point is to the left of the line of reflection, so it reflects so that every point is to the right. Every point moves. However, there are some points on here, like this point, and this point, and this point, and this point, that are to the left of the line of reflection. So they're going to end up to the right. There are other points that are already to the right, they're going to end up to the left. But there are some points that are neither, I want to get rid of that so I don't have to do it next time. There are some points that are neither to the left nor the right. Now, not all of us are great spatial thinkers. But this is what it would look like if we reflected horizontally across the y-axis. These 2 points are invariant. They're 2 points that were on the y-axis to begin with. So if something to the left of the y-axis moves to the right, and anything to the right moves to the left, then it makes sense that on the y-axis won't move. It's an invariant point. If I reflect this same image, or a different location now, but I reflect the same kind of happy face vertically, I can see that some points went from above to below, some points went from below to above, but I have invariant points. So this is showing you the concept of an invariant point. Example 1, and this is what you're going to need the ruler for. We need to graph the resulting function if we reflect that current function across the y-axis. So to begin with, across the y-axis means anything that's over here on the right is going to go over to the left because the y-axis separates left from right. So we can even answer this down here. What type of reflection is this? It's horizontal. It's a horizontal reflection. And I know there are probably some of you that can look at this picture and reflect it in your head and just draw it, bless you. I know that there are some of you that can do that. And if you can do that and get it right all the time, great. But I think for most of us, we need to, myself included, do this systematically. Start on the left, take this point, and say, where will it go when I reflect it across the y-axis? And the key idea here is that it's not going to end up here. It has to end up the same distance away from the y-axis that it was on the other side. Otherwise, you're talking about a funhouse kind of mirror. You understand what I mean by a funhouse mirror? Those mirrors that are all weird and wavy. So when I look at this and I say that it is 4 away from the y-axis on the left, it has to end up 4 away on the right. And what I'm going to do is sweep through these points on the original graph left to right. I've already done that. Now I'm going to go to this one. Well, it's 2 to the left. If I reflect it horizontally, it will be 2 to the right. And then what I want to do is connect them. Notice, by the way, I'm connecting them right to left now because it's been reflected. But that doesn't really matter. I connect them to create a line segment. This line segment reflects to become this line segment. Okay? Okay, and then I move on. I go to the next point. And this is 1 away from the y-axis on the left. It's going to be 1 away on the right. And again, I can connect these. And then I just continue in that fashion. I keep going point to point, left to right, and reconnecting. So this is 2 to the right. It's going to be 2 to the left, and I can connect it. And we have 1 more point to go that is labeled. It is this one. It is 5 to the right, so when I reflect it, it will be 5 to the left. And I connect these, and I want you to notice something. Well, first of all, when you look at the points here, there's 1, 2, 3, 4, 5 points that are labeled. Don't ever make the mistake of thinking there's only 5 points on that graph. There's an infinite number of points. Those are just some key points that we used. I could have put a key point here. And this is 4 away, and if I look at where it lands over here, it's 4 away. So as long as you use the end points of the line segments, it should all work out. Are there any invariant points? Well, I'm going to mark the invariant points. I won't use colors here. I'm going to mark the invariant points with that. Okay? I mean, I think it's pretty clear that the only invariant point is that one. Every other point moved. It may not be entirely clear to you, but that point is invariant because it's a y-intercept. It was not to the left of the y-axis, so it didn't move to the right. It was not to the right, so it didn't move to the left. It's invariant. I mean, I didn't talk about this, but the word invariant means not varying. Constant, fixed. Any questions with one? Again, just like many of our lessons, the early part of the lesson is a warm-up to the ideas. These are not exam questions. On the grid, sketch the result if we reflect that same function across the x-axis, so we should be able to reason out that that will be a vertical reflection. And again, I visualize this in my head, or I look at it on paper, and I look at the fact that vertical means top to bottom or bottom to the top. So how does the top of a shape become the bottom? Well, it has to reflect across the x-axis, which is vertically. So we do the same thing. This is 3 below the x-axis. It's going to reflect 3 above. And I think this next part is pretty basic. I think you see that this whole plateau on the bottom is going to become a plateau on the top. But if I take the next point, it's 3 away below the axis. It becomes 3 away above the axis. And we can go ahead and connect it. This point doesn't move because it's not above, so it's not going to reflect below. It's not below, so it's not going to reflect above. And we can connect this left to right. My next point is this one, which is 2 above, so it's going to be 2 below. And I can connect them. And finally, I have this point, which is 1 below, 1 above, puts it there. Same deal that if we do a decent job of this, we should get that invariant point at x equals 4 because it's not above the line of reflection or below the line of reflection. So invariant points, we'll mark them with the same symbol. Will be here and here. And again, the more general idea is those invariant points lie on the line of reflection. Any questions with example 2? Okay, so we're going to do a little exploration here. And I have the graphs preloaded up here, so you don't need to use your graphing calculator if you don't want to. If I take this function y equals x squared minus 4x minus 5, and I replace every x with negative 1 multiplied by x, how does the transform function compare? Well, if we're going to graph the transform function, then we need to write out the equation of the transform function. So the original function is this. O for original. The transformed function, t for transformed, would be y equals, now I've mentioned this before in other classes that I've had you in, and if I haven't had you in this class, I believe I've already mentioned it at least once here. When you substitute, you always put brackets. Always. You don't need to always, but always putting it is always right. Never putting it is sometimes wrong. Okay? Cover your bases and always do it right. Minus 4 times negative x minus 5. One of the other things I believe I've told you, but I may not have in this class, is when you're doing algebra, don't work left to right. Work top to bottom. I don't have a lot of room here, so what I'm telling you is don't ever do this. We want to simplify that. Don't go equals and have like a run-on mathematical statement. I don't have a lot of room here, so I'm just going to separate these two ideas. If I simplify this, negative x quantity squared, that's how we say negative x in brackets squared. Negative x quantity squared is x squared. And negative 4 times negative x is positive 4x, and then we have minus 5. When you square a negative, you're taking that negative thing and multiplying it by itself, so you get a positive. Anytime the exponent on a negative base is even, you get a positive. Goes back to grade 9 and 10. So this is the function we want to draw. Well, again, I have the graphs up here. There's the original function. You can see the equation of it, x squared minus 4x minus 5. And here is the new function, and you can see the equation of it. I decided when I entered this not to simplify it. I want you to see that the x has become negative x. Okay? But we could simplify that and write positive x squared plus 4x minus 5. What type of reflection is this? Well, it's horizontal. I mean, if I take a look at this point here, on the original graph, it's at 2, 7. On the transformed, actually the other way around. On the original, it's negative 2, 7. On the transformed, it's positive 2, 7. It's flipped over, hasn't it? If I were to take a look at this point, where is it? Oh, it's down here. On the original, it's an x-intercept of negative 1. On the transformed, it's an x-intercept of positive 1. So this is a horizontal reflection. And much like with what we did in the first section, we want to go from concrete to more conceptual and abstract in this course. We shouldn't have to look at a graph. In fact, you're going to see lots of questions where we can't look at a graph because you don't know the equation. The idea here is that since this is a horizontal reflection, so the answer to this question is it's a horizontal reflection. If we want to do the mapping now, we want to go away from looking at a graph and taking a ruler and reflecting points and say, wait a minute, anytime a point reflects horizontally, the x-coordinate flips. If the x-coordinate was negative 8, the new x-coordinate is positive 8. If the x-coordinate was positive 3, the new x-coordinate is negative 3. In fact, I'm going to give you the mapping right now for x comma y. This is the mapping. This is what happens when you horizontally reflect any point. It goes from x comma y to negative x comma y. Now, I want to be cautious here. I want to be cautious here about what you may think that statement in green at the bottom of the screen means. It doesn't mean every x-coordinate is negative. It means every x-coordinate is the negative of what it was, right? So here I have an x-coordinate of negative 2, 7. According to this mapping, it should become negative 2, 7. All it's saying is you're taking negative 1 times the x-coordinate. And I wouldn't even write this. I would just write 2, 7. Well, if I'm telling you that every x-coordinate gets multiplied by negative 1, if I take 0, which is the x-coordinate of the second point, and multiply by negative 1, I still get 0. Well, guess what that point is? That's a y-intercept. And it's on the y-axis, which is the line of reflection, so it doesn't move. And I hope you understand I'm just picking some random points here. Now I want to point something out to you. Does anybody have any questions about that? I want to go back in time here and say that when we change x to x plus 3 in an equation. So I'm talking about horizontal translations, not reflections. Which way is the function shifted, left or right? What do you think?
Right.
Left. Because it's x minus h. And by the way, you got all these questions right on the quiz yesterday. The problem is now you're thinking of reflections, and all of a sudden I go back and I say, well, we've got translations. Don't forget, this is x minus h. So this is an h that must be negative. So it shifts to the left. Are you guys okay with me saying it shifts to the left? Okay. Here's the point I want to make. When I change x to x plus 3 in an equation, the mapping is that. With translations, what I do to x in the equation is opposite to what happens to x in the graph. But With reflections, it's the same. If I multiply x by negative 1 in the equation, every x in the function on the graph gets multiplied by negative 1. All right, let's take a look now at a similar kind of question. If I replace every y in this same function's equation with negative y, then it becomes this. But we all know that we really don't like to write negative y equals. So I want to write positive y equals. And there are a number of ways I can do that. I could just multiply both sides of the equation by negative 1. I could divide everything in the equation by negative 1, or I could move everything on the left to the right and everything on the right to the left. But I end up with the following. Just roll that around and make sure it makes sense in your head. I think you can probably guess what's going to happen here. It's going to be vertically reflected. But let's confirm that. So there's the original function y equals x squared minus 4x minus 5. The reflected function, or the new function, I guess, is y equals negative x squared plus 4x plus 5. And you can see it's reflected vertically. So for example, the vertex of the original parabola is at the bottom of the screen. That's a red point. And the vertex of the new one is at the top, and it's the same distance away. On the other hand, the y-intercept switches. However, do I have negative 5? I don't. Yeah, I do. Negative 1, I don't have. Oh, there it is. That would be invariant. I don't have up here 6, 0 or 5, 0, unfortunately, but 5, 0 would also be invariant. So we can answer this question now. It is a vertical reflection. And I'm doing this with a parabola, but it could be any function. You can see by looking at those graphs that what happens is this. Again, what we did to y in the equation happens to equal what happens to y in the function. So all of the y coordinates switch. This would become negative 2, negative 7. This would become negative 1, well, if I take 0 and I switch it or flip it, since it's a neutral thing, it doesn't change signs. The positive y's become negative, the negative y's become positive. 0 is neither positive nor negative, so it doesn't change. Any questions with that? Still pretty basic stuff, I think. So if we take a look at the summaries, I'm going to walk you through the summaries here, and then we'll look at a few more examples together. During a horizontal reflection, the x-coordinate on every graph is multiplied by negative 1. So positive values of x become negative, negative values become positive. If we're talking about only a horizontal reflection, then the y-coordinate does not change. Well, unless we're talking about a horizontal reflection followed by a vertical translation. Then things would change. How do we achieve this? What we do is we replace every x in the function by negative x. So this is the transformation that we're talking about here. Y equals f of x becoming g of x equals f of negative x, or y equals f of negative x. A horizontal reflection, which is what this is, will always occur across the y-axis, and for some reason, it's not in your notes. That in the summary part, it doesn't actually say x equals 0, I think. Did I miss it? Okay. I've made a note to put it in my next version of this note package. So it's a horizontal reflection across the vertical axis, which has an equation of x equals 0. Invariant points will be y-intercepts. Why are the y-intercepts invariant? Because they're on the line of reflection. And the mapping as x comma y becomes negative x comma y. We take a look at vertical reflections. Vertical reflections occur whenever, I'm going to back up. If you take a look at the top statement here, the top statement says that the replacement in the equation is x becomes negative x. And if you look at the bottom statement says x on the graph becomes negative x. Again, the replacement in the equation is the same as what happens to x on the graph. Okay, it's not backwards. Vertical reflections, we multiply every y in the function by -1. This is accomplished, and the x-coordinate doesn't change, but this is accomplished by doing this. So the transformation is y equals f of x turns into negative y equals f of x, but we don't write this. We don't walk around using this language, negative y equals. We like to say y equals. So if I multiply both sides by -1, this is the idea. And it's useful here to understand that rather than me saying that y is multiplied by -1, since y is the function, the whole function is multiplied by -1. Anytime you see a -1 in front of the function, we're talking about a vertical reflection. It's across the x-axis. The equation of the x-axis is y equals 0, and even as I say that, I'm picturing it in my head and reasoning it out. And again, I don't believe I put that in your notes. For some reason, I didn't type that out. Let me say again, this mistake of a student writing x equals 0 because it's the x-axis, which would be wrong. I'm not saying it's an incredibly common mistake. That's not what I'm saying. Most of you will not make this mistake. But I feel as though none of you should make this mistake. I think the basic concept here is that important, that none of you should make this mistake, and a few always do. So again, my dream is nobody makes it. And invariant points are points on the line of reflection, which would be on the line of symmetry, which would be on the x-axis. And the mapping is this. And that's it in a nutshell. So let's take a look at some examples here. A function has intercepts at particular points. What are the intercepts of the following functions? Well, let's do this from a purely analytical standpoint, without much thought. In other words, we're going to let the math do the work. You should know that this is a vertical reflection. You should know that for a vertical reflection, this is the mapping that takes place. Right? Now what I'm about to write, don't write down until I tell you to. What that means is that this point is going to become 0, -5. Is that 0, -5? And you might need to visualize a graph, and I've put a graph there for you to help you with this part. Is 0, -5 an x-intercept or a y-intercept? What do you think, Alina? X is 0, so y-intercept. And you probably remembered that y-intercepts are always where x equals 0, x-intercepts are always where y equals 0. So this is a y-intercept. And now you can write it down. I just wrote it up there so you can see how I'm getting it. By the way, another way to look at this, and I'm not really a big fan of using the graph. In fact, I didn't even want to put that graph on there for you. You ought to be able to even just sketch it if you need to. Another way of looking at this is to say that this is a y-intercept of 5. If I reflect it vertically, the new y-intercept will be negative 5. And by the way, when we write at this level y-intercept, don't write negative 5. Write y-intercept equals 0, comma, negative 5. If I use this rule of mapping, x comma y turns to x comma negative y here, then this point doesn't change because negative 1 times 0, which is the y-coordinate, is the same. And since y is 0, that's an x-intercept. Similarly here, this will not change because I'm only multiplying y by negative 1 for a, and that means that this will be the point that will be an x-intercept as well. Now, certainly, everybody, what you could have done is you could have plotted these points You don't know what the function looks like, but you could have plotted those points and said, where will those points land if I reflect everything vertically? And if I reflect everything vertically, these 2 points here and here will not move. This point, of course, will move down to here, and then you could have read the coordinates. I don't think you want to go to the concrete kind of right away. You want to try to challenge yourself to think abstractly. What are the x-intercepts here? Well, this is a horizontal reflection. Now, I'm going to do this one a little bit differently, not because it's horizontal. I just want to show you a different way to do it. I'm not going to plot the points on the graph, but I'm going to recognize that this is a y-intercept. 0, 5 is a y-intercept. If I reflect a y-intercept horizontally, which is what we're talking about in B, if I reflect a y-intercept 0, 5 horizontally, which is what we're talking about in B, it will not move because it's on the y-axis. It's on the line of reflection. Whereas if I take my 2 x-intercepts, which are here and here, the tip of my nose is the origin. I have an x-intercept of -2 and +4. If I reflect that horizontally, the -2 becomes +2, the +4 becomes -4. So I don't really think you have to do it in any one particular way. If this were a written response, and it would be a pretty measly written response, you would really have to explain things here. Why is it that you did what you did? And I think by doing the mapping instead of what I just did takes the need for explanation out of it. All right. Well, this one is our first foray into the fact that we can have a horizontal and a vertical reflection. Because x is being multiplied by -1, it's a horizontal reflection. The whole function is being multiplied by 1, it's a vertical reflection. What's happening here is x comma y. Well, the x changes to -x because of the horizontal reflection, and the y changes to -y because of the vertical reflection. And here's where I do want to look at the graph and show you what happens here. No, I'm not going to. If you reflect something horizontally, every point that's to the left of the x-axis will be to the right, and every one to the right will be to the left. If you then take all of those points, wherever they are, and reflect it vertically, everything above the x-axis becomes negative, and everything below becomes positive for y. So we're switching x and y. If I switch this, it stays as 0. If I switch this, it becomes -5. The reason why the x-coordinate The reason why the x-coordinate didn't change is the only thing that can change the x-coordinate in this example is anything that's horizontal, but it's invariant horizontally. If we take these 2 points and swap the x's from positive to negative and negative to positive, they become these numbers. And if I multiply the y-coordinates by -1, they happen to stay the same. Any questions with that example? You know, could x and y both change? Yes. The point just can't be on an axis. All right, a couple more quick questions. Example 4, what's the equation of the resulting transformation if I reflect this function across the x-axis? First of all, you can use the terminology reflected in the x-axis, across the x-axis, about the x-axis, with respect to the x-axis. It doesn't matter. You should understand it's vertical. It's a vertical reflection. And again, you know, I'm picturing the x-axis. It's a line that looks like how I'm holding my arm. If I reflect it across that, things above go below, things below go above. Above to below is a vertical idea. And since this is a vertical reflection, the new function is this. I would like you to kind of take the concept of writing negative y equals f of x and throw it in the garbage. I don't think it's that useful. I think it's it's somewhat useful, but it's more important to just remember a vertical reflection, you multiply the whole function by -1. So this becomes y equals -1 times 3x minus 2. I want to make sure you understand something here. Negative f of x means -1 multiplied by f of x, right? We don't leave it like that. What we're going to do is distribute this and get y equals -3x plus 2. And that's it. Reflection in the y-axis means it is going to become this. And again, there's little subtleties to this. By the time we're done with this unit, you're going to have like a dozen or so things to know. And the concept of trying to memorize those things is, I think, a non-starter for most people. That's not how, when I say most, 99.9% of math students, they don't memorize things. They understand the math and they think about it when they need to. So across the y-axis, I picture a vertical line, which is the y-axis. I say to the left becomes to the right becomes to the left. Left to right to left is horizontal, so it's x that's being messed around with. And that means since f of x is x to the 4 minus 3x, f of negative x is negative x to the 4 minus 3 times negative x, which gives us x to the 4 plus 3x. It becomes plus 3x because negative 3 multiplied by negative x, a negative times a negative is a positive. It becomes x to the 4 because negative x to the 4 means this. And this multiplies to give a positive, and this multiplies to give a positive. Again, it's an even exponent, so you're going to get a positive result. I'm not going to show you the graphs. If you want, you could certainly graph the original function and the transformed function and see that it is a horizontal reflection. I guess I can show it to you. Kind of looked at that and thought, oh, I'll save some time, but it's not that much time. Here's the original graph, kind of a weird looking graph. It's a polynomial function. We have a whole unit on those. And here's the resulting graph in B. For A, which we said was a vertical reflection in A. Yep. Here's the original graph. Here's the transformed graph. How many of you look at that and go, isn't that also a horizontal reflection? Anybody? It is, but it's not across the y-axis. If it were a horizontal reflection across the y-axis, then this point would be invariant. It would actually be there if it were across the y-axis. All right, I think we have one more question. Describe how the graph of the first function compares to the graph of the second. Let's start with B. B is, boy, if somebody wants to give you marks on an exam, like literally go, here's a mark, this is it. This is a horizontal reflection because x in the original graph became negative x in the new graph. And I don't know how important this next statement is or this next little point is, but when I say that y equals 4 to the negative x is a horizontal reflection of y equals 4 to the positive x, I could also say y equals 4 to the positive x is a horizontal reflection of 4 to the negative x. They're reflections of each other. This is a, well, you know what we could do? We could take a look at A and say, if this was horizontal, if it was horizontal, then we would end up with this. This is horizontal. I'm not claiming it is. I'm saying if it were horizontal, that would be what we would get. Do we get negative x cubed? Yes. Because negative x quantity cubed is the same as negative 1 times x cubed, because this is negative x times negative x times negative x, and 3 negatives multiplied together give you the negative 1, and then the x cubed is there. But this is not horizontal, because if it were, this would not be positive 2x squared. It would be negative 2 times negative x quantity squared, and this is x squared. So you would get minus 2x squared. And not everybody can see that without writing it down. So this is not horizontal. This is vertical. And you can tell it's vertical because the positive x cubed became negative x cubed, and the negative 2x squared became positive x squared. Everything has been multiplied by negative 1 in the function. So this is a vertical reflection. Just to show you the graphs, there's the original graph in A. Here is the equation. I don't have the legend up there so you can see, but I'm not hiding anything from you. I've typed in the functions that are given in question 4. Definitely a vertical reflection. This is y equals 4 to the x. There's some business going on here that we will learn about in Unit 5. It's called an exponential growth function. Here is 4 to the negative x. It's a horizontal reflection. Pretty basic stuff, but some things that you could certainly, example 5 I meant to say earlier, things that you could certainly stumble over.